Here are solutions to homework set number 3 for ECE 111. This homework set looks at trigonometry, stuff you cover in Math 105. The first problem is add vectors together. So what I've got is I have, here's x, y, if this is 0 degrees, 90 degrees. I've got 22 at 77 degrees, plus 17 at minus 38, plus 12 at 19. Where do I wind up? Well, there's a couple ways to solve this. In Matlab, I can convert to the x and y coordinates. The x coordinates of the first term is 22 cosine. The y coordinates 22 sine. And you have to remember that Matlab's default units are radians, so I have to convert degrees to radians. Then it works out. Do that for the second term, the third term, add the x terms together, add the y terms together, and this is where I wind up. A second way to solve is to use an HP42 calculator. In my opinion, the best calculator ever made. I can do that by switching over to polar. The seconds, modes, polar. Input the first number, 22, enter 77, complex. There's 22 at 77 degrees. Let's see. 17 at minus 38, complex. Add these two together. Plus 12 at 19 degrees. 12 at 19 degrees, complex, add, and there's your answer. This is the answer in polar form. Go back to rectangular. There's the answer in rectangular form. Let's see. So anyway, that's first one. Problem 2. Same idea. Add these vectors together. In Matlab, I can add them by converting to rectangular form, the x and y coordinates. The x's add up, the y's add up, or with an HP42. Input the numbers in polar form, add them all up, and I get the same answer. Problem 3 is where is B relative to A? So I want to find out where the second vector is relative to A, or in other words, what is B minus A? Well, in rectangular coordinates, subtract the x value, subtract the y value, I get the difference. On an HP42, take the two vectors, subtract them. There's the distance between them in polar form. It's 13.5 meters away at 62 degrees. Problem 4 looks at plotting polar functions. Now Matlab only plots in rectangular coordinates, so the trick is to convert the polar form to rectangular form, then I can plot it. That's the plot command right here. It's always x versus y, not r versus theta. So if I have a function like r equals sine of q minus 1, I've got to find the x coordinate, that's r cosine theta, the y coordinate, r sine theta, then I can plot it. The trick here is I first have to define theta. So let's go from 0 to 6 pi. 2 pi's all the way around. I'm doing around 3 times for no apparent reason. Steps of 0.01. Calculate the radius. Then Matlab is a matrix language. When I multiply these vectors together, I have to use dot times. That tells Matlab, don't treat this like a matrix multiply, treat it like a bunch of individual multiplies. And when you do that, no surprise, you get a circle. Trigonometry, sine and cosine, is all about circles. Part B, let's do r equals theta cubed over 7,000. So again, I'll first define theta, going from 0 to 6 pi. Again, 2 pi's all the way around, so we'll go around 3 times. R is q cubed over 7,000. Find the x coordinate, find the y coordinate, plot it. So this is what that function looks like. Part C, if r is theta times theta minus 6 pi, given theta, calculate r, find the x value, find the y value. That's what this plots as. So in polar form, you can create some kind of pretty functions. To plot them in Matlab, I have to convert back to x and y. Where this applies, if I have a robot, I've got 3 links. I want to know where is the tip given the joint angles. So forward kinematics is given theta, find x and y. To do that, these are the equations. I can do that as a function in Matlab. I'm going to pass z, which is parsed as these are the three angles. I'll then calculate x1, y1, x2, y2, x3, y3, and then plot it. So these are the x-coordinates, the y-coordinates, do a blue line with dots between them. That's the function. With that, I can now do things like, what is the, let's get backing up. I'm going to take these angles in degrees, convert to radians, because anything in Matlab is radians. Basically, anything English is wrong. Where is the robot if the joint angles are 77 degrees, 4 degrees, minus 75? So what I can do is just say, let's call the subroutine RRR. That's rotational joint, rotational joint, rotational joint, RRR, with these three parameters. And it kicks back. Here's the tip. The tip is 0.9 meters x, 1.15 meters y. Or given three different angles. So here's the first angle, 127 degrees. The second angle is minus 53 degrees. So this is 0 degrees, this is minus 53. Third angle is 118, so this is 0, this is 118 degrees. That's where I wind up, at minus 0.82 plus 0.83. That's called forward kinematics. It's all about using trigonometry. A tougher problem is inverse kinematics. If I know where the tip is, what are the joint angles? Well, this is where the function fminsearch really comes handy. If I want to say what joint angles put me at this spot, what I could do is guess. I'm going to guess theta 1, theta 2, theta 3. When I do that, I have some tip position. Say the error is the distance between the tip position and my target, 1.2, 1.2. Return the error. I can now find the minimum of that function. What joint angles minimize that error? So my first guess is 40, 50, 60 degrees, just a guess. It's going to iterate until it finds the right answer. It says the answer is 14.3, 35.1, 12.7. There's the error, basically 0, saying it found it. So here's my target. These joint angles put you at the target. And note, this answer is not unique. I've got two constraints, 3 degrees of freedom. What that tells you is there's an infinite number of solutions. This is one solution. Your solutions might be different. The acid test is right here. If you plug in those angles, do I get 1.2, 1.2? And that is homework set number 3 for ECE 111 for fall 2024.